So I've already uploaded the lecture material, okay, into the e-learning yesterday. Do you have any question regarding our lecture yesterday? Anybody has any question regarding our lecture yesterday? What did we discuss yesterday? Can somebody tell me what did we discuss yesterday? Nobody answering? Can you see the computer screen?
Yes, we can.
Okay. Okay, let's review what we have discussed yesterday. We discussed yesterday there are two types of derivatives for vector fields. One is called divergence and the other is called curl, right? So the divergence of a vector field is a scalar function, while the curl of a vector field results in vectors, vector. So, okay, we have looked at some L dot vector field F. For curl of vector field F, the notation is del cross vector field F, which can be computed using this determinant approach, a 3 by 3 determinant approach. Yeah? And I showed you, I think, two ways of computing the 3 by 3 determinant. Yeah. And then I discussed you some identities. So one of the identities is the divergence of a curl of a vector field F is always a 0. And also the curl of a gradient F is always a 0 vector. Yeah. And then we discuss one example. So given a vector field F, um, how to find a scalar function phi such that the vector field F is equal to. So this is an important question exercise, because later on when we look at this other concepts of integrals of line integrals, okay, there is an analog of line integrals in vector fields related to the fundamental theorem of calculus. So it is important for us to know, given a vector field F, is it possible to find a function phi such that the vector field F is a gradient of a function phi if it exists. And if it exists, the vector field F is also called is conservative, and the scalar function phi is called the potential function. So there is a test, right, to determine whether the scalar function phi exists, such that the vector field F is equal to the gradient of phi. To the vector field, we need to show that this relationship is satisfied. This relationship written in blue here is satisfied. If it is not satisfied, then the scalar function p does not exist. And this is the case for the vector field in 3D space. For to check whether whether phi exists such that the vector field is equal to the gradient of phi. There's a set of three equations here. Okay, if all these three equations are satisfied, then we can conclude that there exists a scalar function phi such that the vector field f is equal to gradient of phi. Yeah. And also we look at one example where the gradient, the scalar function does not exist. Yeah. I showed you this arc length formula, line integrals. And then next, we move on to discuss. I introduce you this concept of line integral related to not yet. I haven't introduced you the concept of line integral. No, not yet. Huh? Yeah. I discussed with you this the arc length formula. Okay, for a curve in space. Okay. Suppose we have a position vector r of t. Then the curve it describes a curve in space. Yeah. So the length of the curve in space can be written as the integral a to b can be written in this form here. The integral a to b, the square root of x prime squared plus y prime squared plus z prime squared dt. So this is a generalization of a arc length of a curve on a plane. Okay. If you recall, to find the arc length of a curve in a plane, it is the square root of a to b, square root of, the integral a to b of square root of x prime squared plus y prime squared only. But for a curve in space, we also have this additional term plus z prime squared dt. And then we look at some examples. I showed you some examples of an example of evaluating arc length of a curve represented by a vector function. Okay, let's now wish to introduce to you another integral related. Okay, suppose we have this wire, a very thin wire, represented a very thin wire in 3D space, represented by this position vector RT. Want to find the mass of a thin wire with uniform density. Suppose the wire has a uniform density. That means the density is constant throughout this wire gamma. So density is of a wire is a mass of a wire times the length of wire. Okay, we can determine the length of the wire from the previous integral formula. So mass is then density of wire times the length of the wire, right? Now, if the density is uniform, if the wire has a uniform density, so density is some constant rho. And we have seen just now, the length of gamma is equal to this integral a to b of this square root dt. Yeah, can also be written in terms of so this square root is same as the modulus of the r prime t, and then it is also well, it can also be written as the integral of 1 over gamma over the curve gamma ds, where s is the arc length element here. Okay, where s here is an arc length element. This is the arc length element. Okay. So from the previous page, S is the arc length element. ds is equal to the modulus of r prime t dt. Okay. So using this relationship, we can write the mass as the integral of 1 over this curve gamma. So now we have an integral over a curve. Okay, previously we have integral over interval, integral over a region. When we talk about double integral, we discuss integral over a region, and we discuss triple integral also. It is a triple integral over a solid object or solid region. But now this is a different kind of integral. It is an integral over a curve gamma in space. Yeah. So this is also called a line integral here. Density. What if the density of the wire varies from point to point? Okay, so again we use this estimate approach. We use an estimate approach. Suppose we have a very thin wire in the shape of a curve gamma with density at any point x, y, z on gamma is given by f x, y, z. Okay, maybe I can, in some book they use the density function as a delta x, y, z. Yeah. So how to determine the total mass of a thin wire with varying density? So again, we use the same estimation approach that we have seen before. We will partition this thin wire into small sub wires here. Okay, into small sub wires here. And so on. And suppose the last point is Pn. So in other words, we partition this small thin wire, green wire here, into n small sub wires. Yeah. And so then let's represent the first sub wire as gamma 1, the second sub wire as gamma 2, and so on until the last sub wire gamma n. So gamma is the sum of the n sub wires here. Okay, so let's focus our attention to this gamma k here. So there are many points between pk minus 1 and pk. So let's choose a representative point of gamma k as xk, yk, zk. Then the density of the wire gamma k is approximately equal to the density at the representative point here gamma k is approximately f, the density function at xk, yk, zk. And what is the length of the wire gamma k? We use the letter S, isn't it? So let's denote the length of the wire gamma k as delta sk. So we find the mass of each of these gamma 1, gamma 2 until gamma n, and then the sum, and then we sum them up to get an estimate of the total mass of the wire gamma. Okay, so the mass of wire gamma k, mass is density times length, right? So the mass of this wire gamma k is approximately the density at the representative point xk, yk, zk times the length of gamma k, which is delta sk here. So what is the mass of the total of the mass of each gamma 1, gamma 2 up to gamma n? Okay, so this So this is the summation then that approximate the actual mass of the wire gamma. To get better and better estimate, okay, we we divide the curve into smaller and smaller partitions. Yeah, to get better and better estimates, we divide wire gamma into smaller and smaller partitions. But then that will increase the number of partitions. So we define the actual mass of the wire gamma is by letting n here tends to infinity. Okay, when n tends to infinity, of course, the arc length element goes to 0. But if this limit exists, then we denote it as this line integral of f x y z over the curve element. So this integral is called the line integral of a scalar function f x y z over gamma. Yeah. So this is a new type of integral now we are looking at. Okay, a new type of integral which is called the line integral. Yeah. Later we will see a line integral for a vector field. Yeah. Okay, how do we evaluate this line integral here? So the question now is how to evaluate this line integral. So we use the parametrization technique. If a curve gamma has the parametrization has this vector can be represented by this position vector. Okay, so we can think of gamma as the parametrization. Okay, so we can think of t is a means the what the initial point. When t equal to b, give us the end point. Yeah. So the technique is to replace x by xt, replace y by yt, replace z here in the line integral by zt, and then replace the arc length element by this modulus of r prime t dt. Okay, so this is a technique to evaluate a line integral. So let's look at an example. So evaluate the line integral. The curve is sometimes represented. Let's denote the line integral over a curve gamma 9 plus where gamma is parameterized by RT equal to 2t to the power of 3 over 2i plus the t squared vector j, or say t is between 0 up to 1. This is an example of a of a final exam question, sample final exam. Yeah. This is just for evaluation of line integral. Okay, nothing to do with related to mass or anything. This is just a matter of parameterization technique. Yeah. 9 plus 8 square root y ds. Okay, we replace y in the integrand by y of t. And then replace ds by the modulus r prime t dt. And t is from a to 1. Yeah. So what is r prime t? From the given, we are given this rt, okay? So r prime t is equal to what? First, notice that this is xt. The coefficient of I, vector I is xt. The coefficient of t squared here. Okay, t squared. And what is r prime? So differentiate rt with respect to t. The result is 3. 3, we have 3 over 2. What is that? What is 3 over, 3 t to the power of 1 half plus 2tj, right? 2tj. And what is the modulus of that vector? It is the square root of the square of the component. 3t to the power of half squared plus 2t squared, okay, dt. So this reduces to a single integral, a single square root of t squared is t, right? Because t is between 0 and 1. So square root of t squared is t. Next, we have the square root of 9t plus 4t squared dt. Okay? Anybody? How to evaluate this single integral? Any idea? Yes? Where are you? Where is everybody? Anybody? How to evaluate this integral?
Chain rule?
How to apply? We are not differentiating. We are integrating here. What about substitution? Huh? What about substitution? Say u equal to 9t plus 4t squared. And observe that du is 9 plus 8t dt, isn't it? And we do have 9 plus 8t there in the integrand. So this becomes the integral of square root u du. And the limit also transform. When t is 0, u is 0. When t equal to 1, we have 9 plus 4, which is 13. Okay. Now it is easy to integrate square root. is it is what u to the power of 3 over 2 divided by 3 over 2, said that's 2/3 u to the power of 3 over 2. Yeah. So then we substitute the limits. We get 2 times 13 to the power of 3 over 2. Okay, so that is the answer. That is the answer here. You can leave your answer in that form, or can use your calculator also to write the answer in a decimal form. All right. So that is the one example of evaluating a line integral here. Let's do one more example. Suppose we want to suppose C is a line segment in space from say the point 0, 0, 0 to the point 1 minus 3, 2. Okay. We want to evaluate this line integral here. X plus y squared minus 2z ds. Okay. Yeah, so now we have a line integral of a function of 3 variables here. So this is no. See, in this question, the position vector of the curve C is not given. We are only given the initial point and the end point. Right? We are only given the point 0. Suppose this is 0, 0, 0, and we have another point in space with coordinate 1, minus 3, 2. So we have a line here connecting these 2 points. Okay, we have a line connecting these 2 points. Okay, so the curve C is a directed curve. It has an initial point and a terminal point. If you look at our discussion for line integral, the curve is all there's a direction given to this curve. When we parameterize, then the curve has a direction. Okay, when we parameterize the curve, then it has a direction. Okay, what is the parameterization of the curve C here? It's a line segment. So we need to recall something that parameterization of a curve in general, the parameterization of a line from say the point x naught, y naught, z naught to the point say x1, y1, z1 is given by There's a position vector here. Yeah, tx1 plus 1 minus t x naught I plus t y1 plus 1 minus t y naught j plus t z1 plus 1 minus t z naught k. And t for this is always between 0 and 1. Okay, this each component here is linear. Yeah, each component here is linear. So you can check this. When t is 0, it is x0, right? The first component is x0. When t is 0, the second component is y naught. When t is 0, the third component is what? The third component is z naught. Yeah, you can check this that when t is 0, the result is x naught I plus y naught j plus z naught k. And when if I replace t by 1, the result is x1 I okay. So this is R naught is associated to the point x naught, y naught, z naught, while R1 is associated to the point x1, y1, z1. Okay. So as t varies from 0 to 1, the point varies from x naught, y naught, z naught to the point x1, y1, z1. So this is the formula we need to use to find the parametrization of the curve C. So in this example, going back to this our example, we have x naught, y naught, z naught equal to the origin, and x1, y1, z1 equal to the point 1 minus 3, 2. Then, okay, so x naught, y naught, z naught are 0. Then we have t I plus minus 3 t j plus 2t k. Okay, substitute x naught, y naught, z naught, and x1, y1, z1 into this formula for rt here, and t is between 0 and 1. Okay, so now we can evaluate the given integral after we have determined the parametrization. So therefore, the integral of x plus y squared minus 2z ds, use the parametrization technique, y by yt, and replace z by zt, and then we replace s by the modulus of r prime t dt. Okay, so what is xt here? Anybody? What is xt here? T is from 0 to 1. Yeah, for this integral, t is from 0 to 1. Yes. What is xt here? Hmm. Can you hear me?
Yes, Doctor.
Yes, what is xt here? Remember, this the parameterization is xt, okay? According to the formula, according to this formula, the xt yt from the parameterization, from this technique here. Okay, xt, yt, zt, they are the components of the parameterization, rt. So that means you need to compare this. You need to compare this rt with xti plus ytj plus ztk. So what is xt? If you make this comparison, what is xt?
1.
T, Doctor.
T, yeah, it is T. Okay. And then what about yt?
Negative 3t.
Yeah, compare this vector with this vector. So yt is minus
Minus 3t.
3t, yes. And then square, right? Because we have yt squared there. Then minus 2. Okay, what about zt now? Zt is?
Minus 40. Oh,
zt first. Give me zt first.
2t.
2t, yes, 2t. Okay. Okay, next we have the modulus of r prime t. So we have rt there. So minus 3j plus 2k, right? 2k. Yeah. And this modulus is we don't have any t there. It is we don't have any t there. So the modulus is equal to the square root of 1 squared minus 3 squared plus 2 squared, which is equal to the square root of what? 1 plus 9 plus 4, which is 14, right? Yeah. So we can pull out this constant square root 14 outside the integral. And the bracket term simplifies to t. We have t there plus 9t squared and then minus 4t. I'm sure you can evaluate this easily. So please convince yourself that this the value is 3 times square root 14 over 2. Yes. Any question? So that is an example of evaluating line integral over a curve C in 3D space. Yeah. And in some situations, we have the curve C could be a joint of several curves. For example, here in this diagram, the curve gamma is a joint of gamma 1 plus the curve gamma 2 is a joint of several curves here. So then to evaluate the line integral of the scalar function fxyz over the curve gamma is a sum. is the sum of the line integrals over each gamma 1, gamma 2 up to gamma n. Yeah. So let's do an example. Suppose suppose C, the curve of two curves C1 and C2 as shown here. So let me sketch the graph. It is a curve and a semicircle here. Yeah. So the curve or the semicircle is C1, and the curve, the vertical curve is C2. And the point here is it is a semicircle centered at the origin of radius 2. Yeah. So therefore, C is the joint, the sum of two curves, C1 evaluate this line integral 1 plus xy ds. Yeah, this is the question. So we have to evaluate this line integral as a sum of two integrals. Yeah. So we must evaluate this integral as a sum of two integrals, 1 over C1 and the second integral over C2. Yes. So both are line integrals. Yeah? Both integrals over C1 and the integral over C2, they are line integrals here. Evaluate C1. But you need to know the parametrization of C1. Suppose it is equal to R1T. Yeah. It is a circle, right? It is a circle. Recall that for a circle, we have a parametrization. So we have here x1 ti plus y1 tj. The parametrization has that form because this is a curve, a two-dimensional curve. So there is no vector k here. Yeah. So recall something that you have studied before. A circle centered at the origin of radius r has a parametrization xt equal to t is r sine t, isn't it? Yeah. So the semicircle can be parameterized as x1. Here the radius is 2, right? 2. So we have 2 cosine ti plus 2 sine tj. Now this is a circle from -2 to 2. So t is between minus pi over 2 up to pi over 2. Okay? Yeah. So now we can evaluate the integral over C1. we replace 1 by x by xt, replace y by yt, and replace ds by what? Modulus. I'm sorry, we should I r prime 1 t dt. Okay, and t is from minus pi over 2 up to pi over 2 here. So we substitute x1, y1. X1 is 2 cosine t. Y1 is 2 sine t. Okay. And what is R1 prime? Differentiate R1. We get minus 2 sine ti plus 2 cosine t j dt. Okay. Yeah. So then it's just a matter of simplifying of cosine t, sine t, and the absolute value, the modulus is square root of minus 2 sine t squared plus 2 cosine t squared dt. Okay? Yeah. What is that integral? Square root sine equal to? This is equal to what? Square root of 4 sine squared plus 4 cosine squared, right? So I can factor out 4. And sine squared plus cosine squared is always equal to 1. So we have square root 4 equal to 2. So I can pull out the factor 2 outside the integral. Okay, so how to evaluate this 4 cosine t sine t dt? Any idea? Yes? Any idea how to evaluate this single integral here?
Change the cos t sin t to
Uh-huh.
cos 2 sin 2t, right?
Yes.
And then we can easily integrate it.
Yes, yes. Yeah, that's the idea. We rewrite because we know that what? We know that sine cosine t. So 1 plus 4 cosine t sine t is the same as 2 sine 2t, isn't it? It is 1 plus 2 sine 2t. Now we can integrate this easily. The integral of 1 is t. The integral of 2 sine 2t is minus cosine 2t, right? T minus cosine 2t, yeah. So I leave it to you to simplify this, show that it is eventually equal to 2 pi. 2 pi. Yeah. Because we still have another integral to work on, which is the integral over C2. where C2 is this vertical line from point 2 up to minus 2. Okay. So next, we want to evaluate the integral over C2, but first we must determine the parametrization first. Let's call the C2 as R2t equal to x2t I plus y2tj. So what is x2, y2? This is a line segment, right? This is a line segment. If you recall, this is a line segment joining the point here, which is 0. Yeah, this is the line segment C2. Okay, what is the parametrization of a line segment here? Clearly, xt is 0, right? Because it is on this on the y-axis, so it is 0. So so x2t is 0. What about y2t? It is a function t from 0 up to I can write it as t that varies from 2 up to minus 2. Okay, the direction here you must be, or we can write it as minus t, where t varies from. There are many ways of parametrization. Parametrization is not unique. Yeah, so this is one way. So when you can check this, when t equal to minus 2, y2 is equal to 2. When t is equal to 2, yt is equal to minus 2. Okay, so it works. Yeah, so this is equal to 0i, y2 is minus t, minus tj. So r2 is just minus tj, where j is from minus 2, t is from minus 2 to 2. Okay, so now we can evaluate the integral over c2, 1 plus xy. Now we have, say, minus 2 up to 2, 1 plus x2t, y2t, and then ds is the modulus of r prime 2t dt. Okay, so we substitute. X2 is 0, y2 is minus t. What is r2 prime? R2 prime is minus 1 j, right? Minus 1 j. And it is equal to 1. This is just simply 1. Yeah, so it's just an integral minus 2 to 2. The bracket term is 1 dt, so it is t from minus 2 to 2, which is 4, right? 4. So therefore, is the sum of the integral over c1, which is 2 pi, and the integral over c2, the line integral over c2, which is 4. So that is the answer here. Any question? Yes? Now, as I said, the parameterization is this is one way to parameterize C2. But there are many other ways, right? Parameterization is not unique. Relatively, if what did I? Yeah, go to this. Yeah, something like this. Yeah, parameterization. Remember, I discussed this parameterization, joining 2 points in space. I can also use this one, this form. Okay, the parameterization of a line from x0, y0 to x1, y1. Can also use this this formula, but without containing k. Okay, without containing k. So alternatively, can also recall this result. Okay, a line from the point say x0, y0 to the point x1, y1. A line joining from x0 to x0, y0 to x0, y0 can be parameterized by this formula here, RT equal to, let me take a look at the previous formula in green. What do we have? We start with, where is it? Yeah, this TX1, TX1. Tx1 plus 1 minus T x0 I plus T x0 plus 1 minus T no, 1 plus 1 minus T y0 J. And if you use this parameterization, T always lies between 0 and 1. So let's go back to the our diagram for C. Okay, C here, isn't it? It's from the point 0 minus 2 up to this is plus 2 up to the point 0, 2. So you can think of the 0, 2 as the point, the initial point x0, y0. The point, I'm sorry, this is a minus 2 down here. This is minus 2 down here. So this is x1, y1. Okay, x1, y1. Let me write down x1 clearly. So therefore, this is C2 earlier, right? This is C2, R to T. So we can also represent the curve C2 with a different parameterization. R to T, what is it? Tx1. X1 is, I'm sorry, this should be, yeah. X1 is 0, right? 0. Plus 1 minus T x0. X0 is also 0 here. I plus Ty1. Y1 is minus 2 plus 1 minus T y0. Y0 is 2. 0, right? Times vector I. plus simplify this, we get minus 2t plus 2 minus 2tj. So which is 2 minus 4t. 2 minus 4tj. And here, t must be between 0 and 1. So this also, parameterization also is also described the same curve C2. You can see here when t is 0, it gives us 2j. When t equal to 1, we get minus 2j. Yeah? So you can also use this to evaluate the so I leave it to you to show that the integral over C2 to be evaluated using this parameterization. 0 to 1, x is 0, right? Here x is xt is 0, 0, yt is 2 minus 4t, and then we have what? The modulus of r2t, the modulus of r2 prime. Here the modulus here is minus 4, minus 4j dt. Okay, I leave it to you to show that the result is the same as the previous one, which is equal to 4, which is equal to 4. Yeah. You have any question? Any question?
Doctor.
No?
No, doctor. Right now, no.
Okay. So now let's move on to another topic. Uh, the line integrals of a vector field. Okay, the line integrals of a vector field. I want to introduce that through one application, work done by a force. The work done by a force. Something not clearly written here. This is W. Yeah, work done by a force. Remember in a physics course, we have an object here. The initial position is at point P. Okay, by this horizontal force F, the object moves from P to the new position Q. And suppose the distance is D. The distance between the old position and the new position is equal to D. So we have a force that moves this object P to a distance D, right? A distance D. So in physics, work is defined as force times displacement, which is F times D. So here we assume F is constant in the horizontal direction, and D is also a constant. So the work done is for F times D. So if there is no displacement, then the work is 0. Consider no work is done. Okay? Remember this, right? From your physics class in Form 4 or Form 5. Okay? Now suppose the direction of the force is no longer parallel to the motion, to the displacements. Suppose an object particle moves along the line segment P to Q under the influence of a constant force F. See, it's now F is a vector. It has a direction now. And look at this direction is no longer parallel to the direction PQ. Of the force vector F times the displacement PQ. See, PQ now also has a direction. The force is also has a direction. And suppose the angle is theta between the force and the displacement vector. So the work done is defined as the modulus of the vector force vector F times the modulus of the displacement vector PQ times cos theta, where theta is the angle. Yeah. Why? Because we can think of this the modulus of F times cos theta as the magnitude of F along the so the work done is the magnitude of F, okay, along the direction of PQ times the distance PQ. And this can also be, this product of, can also be represented as a dot product of the force vector F with the displacement vector PQ. Okay, because recall that u dot, you have two vectors u and v. U dot v is the same as the modulus of u times the modulus of v times cos theta. Yeah. Yes. Now consider more generally, the force varies from now F becomes a vector field here. Okay, so the force is F, vector F. This is like a vector field now. Varies. Okay, the force varies from point to point. And suppose the object moves or particle moves along the curve, resulting in the particle moving along a curve gamma here, under the influence of the variational force F. Okay, what is the total work done then? Question is, what is the total work done in moving the particle from this initial position to the last position here, where the force is varying, okay, from point to point. Gamma here into several subcurves, gamma 1, gamma 2, gamma k up to gamma n. Okay, we subdivide the curve gamma into n partitions. So let's focus our attention to the curve gamma k here. Now gamma k has many points, so let's choose one representative point, xk, yk, zk. Okay, and suppose the force at the representative point is the vector field F at the point xk, yk, zk. Remember, the force is varying, right? So the work done along the curve gamma k is approximately the force with the displacement. Okay, the displacement denoted here by delta RK. Yeah. Okay, delta RK. It's a displacement. Yeah. Okay, denoted here by delta RK. I hope you can see why. Why is that? I hope you can see why. Yeah. From this point to this point, okay, from this point to this point, there's a displacement of a delta RK. Delta RK. Okay. Yeah. Okay, let me explain that a little bit more. So we have a point here, from here to here. Okay, the position vector here to this position vector here. So the displacement vector is approximately this one here. This is what is called delta RK, this one here. Yeah. Okay. Yeah. So the work done along the curve gamma k is approximately the force, okay, the force vector dot with the displacement vector, according to the previous idea. Yeah, according to this previous idea here. Because for small delta, the curve is almost like a straight line, isn't it? For very small partition, and the curve here, the curve is like a straight line. It's almost like a straight line. Okay, it's almost like a straight line. Where has it gone? Where is that diagram just now? Here. Okay. Yeah, I'm zooming this part, gamma k. I'm zooming that part to this diagram on the right. And then we approximate also the work done along gamma 1, gamma 2, gamma n using the same idea. So the work done, the total work done along the entire curve gamma is approximately the sum. It's approximately the sum of the work done along gamma 1, gamma 2, and up to gamma n. Okay. So to get better and better approximation, we use smaller and smaller partition. So we define the actual work done as the limit as n tends to infinity, okay, of the sum. And if it exists, it is written in the form the integral as a line integral of the vector field f dot dr. Now we have a new integral which is a line integral of a vector field. Okay, this is useful to what? To calculate the work done involving variational force field. Okay, so I've introduced you this concept of line integral of a vector field through this problem of finding the work done. Now, how to evaluate? To evaluate, again with the help of parametrization. If we can come up with the parametrization of the curve gamma as RT equal to XTI plus YTJ plus ZTK, T is from A to B, then we replace X here by XT, okay, in the vector field F. We replace X here by XT, replace Y here by YT, replace Z by ZT, and then we replace dr here by dr dt times dt. And remember, this is again a dot product. The dot that you see here is a dot. It's a dot product. It's just not a dot, but it is a dot product. Okay, this one here. RDT is a vector, and the vector field F is also a vector. Okay, so we have a dot product of two vectors there. So this is how we can calculate the line integral of a vector field. Okay, let's see an example. For my notes, where did I put it? Strange. Where is? So excuse me, I can't find the notes related to this. Okay, I got it. Okay, I found it. Suppose a particle moves along a curve parameterized by RT equal to cosine t I plus sine t j plus tk. This is actually a helix, spiral helix. T is from 0 up to 2 pi under the influence under the influence of a what happened here? Under the influence of a force F, so force field represented by the vector f x y z equal to minus zy I plus zxj plus xyk. Okay, determine, here is the question. Determine the work by the given force. By the given force. By the given force. Okay, this is the question. So we know now that the work done is given by the line integral. The work done that's represented is W by the integral over the curve gamma. It is what? F xyz dot dr. Okay, dot dr. This is a dot product. So make sure you write the dot clearly. Don't if you miss the dot, of two vectors. So since the parametrization of the curve is given, so we calculate it as we replace replace x by xt, replace y by yt, replace z by zt, and then this becomes the dot product of dr dt times dt. Okay, that is the parametrization technique. And t varies here from 0 up to 2 pi. So look at the vector field F. Okay. Now look at the given vector z by, we have minus zy. So we replace z by zt, y by yt, and then we have zxj. Replace z by zt, x by xt, and then we have xyk. We replace x by xt, y by yt, times the vector k, times the vector k, and dr dt. Okay, what is dr dt? Look at the vector given. Look at rt. So we differentiate rt to get r prime t. So we get a minus sine t plus k, plus the vector k times dt. Okay. So what is xt, yt, zt? It's from this given rt. Okay, we want to associate this rt with xti plus ytj plus ztk. Okay, so this implies that xt is equal to cosine t and yt is equal to sine t and zt equal to t. So we substitute this xt, yt, zt here in this integrand. So okay, zt is t, yt is sine t, zt is t again, and xt is cosine t. J. Then we have xt again, which is cosine t. Yt is sine t. K. Okay, and then we dot this vector with the vector minus sine ti plus cosine tj plus k. Yeah. Which is okay. So now we determine the dot product. Remember how to determine the dot product of two vectors? First, we multiply the component I times the component I with the of the first vector times the component I of the second vector. So that gives t sine squared, isn't it? So we get t sine squared t. And then we multiply this component j of the first vector with the component j of the second vector. So we get plus t cosine squared t. And then with the component k of the second vector. Okay, so the result is cosine sine t plus cosine t sine t. See, so now after simplifying, it is a single integral of it reduces to a single integral of with respect to t. Okay, so notice that cosine squared t plus sine squared t is equal to 1. So I can further simplify the first two terms as t. So then we have this single integral. Sine t can also be written as what? Using the identity again, this is sine 2t over 2, isn't it? Cosine t sine t is the same as sine 2t over 2. Yeah, so then we have sine 2t over 2 here. Okay, so now we are ready to perform the integration. The integral of 2 is t squared over 2. The integral of sine 2t is minus minus cosine 2t over 2. Then we evaluate this t from 0 up to 2 pi. Okay, I leave it to you to show that the result is the same as 2 pi squared. 2 pi squared. What is the unit for work usually? Anybody? What is the unit for work? You are rather quiet today. I wonder why.
It's joules, sir.
Joel, Joel, yeah. Why are you so quiet today? You have a test tonight or what? Huh? You have problem hearing me speaking? Is that it?
Sometimes you were laggy, so maybe that's why.
Oh, really?
Yes, Doctor.
Yes.
I wonder if my internet
Uh-huh.
is not working, but I think your voice is
Oh, really?
lagging quite a bit. But right now it's
Oh.
okay.
Maybe it slows things down a little bit, yeah. Okay, so that's the new line integral with respect to a vector field. Yeah, one application is finding the work done. Okay, so next is the fundamental. Okay, next I will show you. In calculus we have this fundamental theorem, right, of calculus. So we also have a fundamental theorem for line integral. Okay, that I will discuss tomorrow. Remember, tomorrow we have a makeup class, right? Yeah, I will discuss that tomorrow with you tomorrow night. We have a makeup class tomorrow. Tomorrow, Thursday night, 8 p.m. Say maybe until 9:30 p.m. Tomorrow is 10th of June. Okay, so please take note of this. So what I will discuss tomorrow is this. Look at our course information. Course information. Line integrals in scalar and vector fields. I've also discussed with you these potential functions and conservative fields. So tomorrow, I will discuss this path independence. Path independence as well as Green's theorem here. This is what I will discuss tomorrow. Path independence. Here you need to recall back how to recover a scalar function from the gradient. Yeah. So that will simplify. If the vector field f here is if the vector field f here has can be written, if the vector field f here, okay, if the vector field f here can be written as a gradient, if the vector field f here is conservative, that means it can be written as a gradient of a scalar. Greatly for the evaluation of line integral vector field. Okay, yeah. So it is equivalent to the fundamental theorem of calculus that you have studied before, yeah, for functions of a single variable. So that I will discuss with you tomorrow night. Yeah. Okay, enough for today. So thank you for your attention. So let's me show you the the course, the QR code for your attendance. It's taking longer time than usual. Okay, here it is.
Doctor,
Yes.
the submission link for hand info haven't created yet.
Okay, thank you. Thank you for reminding me. Okay, I will create. It is due today, tomorrow, right?
Tomorrow.
Tomorrow. Okay, I will create the portal for your hand in for submission. Thank you. Okay, here is the QR code for your class today. Thank you once again for you may leave after you have finished scanning. And don't forget tomorrow night, 8 o'clock, is we have a makeup class.
Thank you, Doctor.
Okay, thank you.
Thank you, Doctor.
Thank you.